Hello and welcome to this video about determinant proofs. In this video, I'll be completing this proof that I started last time. I was able to prove part A without using parts B or C, since in the online proof they proved parts B and C first and then used these to prove part A. I'm sort of doing it the other way around. I'm using part A to prove part B, and part C is easily proven without using parts A or B. So now to prove part B, that this formula is true for the cofactors of these matrices when I isn't equal to m. That means we'll leave the row with different entries in the minors of these matrices. So now to start this proof, we'll start with the left-hand side and expand it out using the definition of the cofactor. We can get this expression in terms of the minors of B and C because the row with entries that are different in all matrices are left in the minors. And so these matrices obey lemma 1DA. So let's have a deeper look at what's happening when we calculate the minor of A. Eliminating row I and column J, we're deleting the row and column that are circled in red. When we do this, we're left with this matrix. The red lines show where this column and row have been, but the row with entries that are the sum of the entries of matrices B and C are left in this minor, because they're in row M. So these matrices are of the form so that they'll obey lemma D1 part A. We can then expand the brackets giving us this expression. So then we can use the definition of cofactors in the forwards direction this time to get the result which proves part B. So now to prove part C, which is the last part of this proof, we'll prove this equality. To prove this statement, we'll start with the left-hand side and expand it out using the definition of cofactors in the reverse direction. We can then substitute B in for A directly, because we've removed row M, which contained all of the entries that were different for these matrices, leaving us with identical matrices. So let's have a look at a picture of this. The minor function removes all of the entries circled in red, depending on the subscripts of this function. Now, since we've removed row M that contained all of the entries that were different, matrix A contains no entries that are different to matrix B's entries, or even matrix C's entries. So now this minor matrix is equal to the equivalent minor matrix of B. We can now use the definition of cofactors in reverse to get the cofactor of B, which proves it true for part of part C. We can use exactly the same reasoning to prove it true for the minor of matrix C, because we've removed row M that contained the only unequal entries in this matrix. And then finally we can use this definition in reverse and prove it true for matrix C, thereby completing the whole proof. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.